Bah, en fait, c'est dans ton zoom, juste tu vas la couper comme tu veux. Tu peux la lancer et la couper comme tu veux. Le son, tu l'as mis sur le HDMI, là, tu vas me virer ça. Euh, speaker. Ouais. Je les vois, alors. Speaker, en fait, tu t'en mets pas bah ouais, parce qu'il n'y a personne. Cherche le son. Ouais. Mais c'est la sortie qu'il faut. Ouais. Et bah, tu vois, voilà, là, c'est pas X280, il y a 200. Voilà, c'est ça. Ouais, tu peux ça.
Mais c'est juste pour éviter que ça enregistre pendant une heure.
Oui, oui. Non, mais là maintenant, tu peux tout couper et juste, tu n'as plus qu'à cliquer dessus et c'est bon. Tu vois ce que je veux dire?
Ouais, ce sera plus le même lien YouTube, non?
Non, 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 quand je dis tout couper, c'est juste que là.
Okay, so we can start. Hello everyone, and welcome to the PhD defense of Fournier, titled Parallelizable Training in Deep Learning through Local and Distributed Approaches. So we have the jury composed of viewers, so Olivier Beaumont, Research Director at MERIA, Larry, also Research Director at MERIA, and we have two examiners, so Julia Bussac, researcher at MERIA, Eugene Belibowski, assistant professor at Concordia University, and Edouard Yallon, the director of the PhD, and myself, professor at Sorbonne University. So we have the floor, about 45 minutes to the only work, and then we switch to the Q&A session.
Okay. So thank you everyone for being here at my PhD defense, which has been supervised by Edouard Yallon and prepared with the MEI team of the IZIR lab at Sorbonne University. We also want to thank the Sorbonne Center for Artificial Intelligence and the ANF Adonis for their funding. Deep learning has made a significant stride in the last decade. It is used to train deep neural networks, DNNs, which are computational machines parameterized by billions of parameters that train large datasets. We have seen recently a move from smaller task-oriented deep neural networks, such as to play board games, for instance, to now larger and more generic foundation models, which are trained on a large amount of multimodal data and then can be refined for finer tasks. But this rise in performance also has a rise in training computational costs. Indeed, to improve the performance of the deep neural network, you need to both increase the dataset sizes and the parameter sizes. Thus, this will require more training resources and thus more time and energy to train them. Empirically, the training compute of most modern foundational models in the last decade has indeed followed an empirical exponential curve. There are several ways to mitigate this increase. The first one is to improve the hardware by using faster GPUs or TPUs, which are the devices used to train neural networks. This has allowed for now such networks to continue this exponential increase. It is also possible to improve the dataset quality by removing low-quality examples or improving deep neural network architectures directly by using more scalable architectures like transformers or more efficient ones like mixture of extents. The approach that we are going to take here is to improve directly the training procedure. As a quick reminder of how deep neural networks are trained, we have a training loss that we want to minimize using predictions of the network and examples of the dataset. This is generally done with a gradient descent. We first need to estimate the gradients of the training loss with regard to the parameters of the deep neural network. This is done generally with backpropagation, which is done in two passes. In the first pass, the forward pass, we first sample a millibatch of data, and each layer will compute, store, and propagate what are called activations to its next layers, successively from the first to last layer. This gives, at the end, a training loss, depending on the prediction of the network. Then, in the backward pass, the reverse order is used to compute the gradients. Starting from the training loss and using the activations which are stored inside the buffers of the layers, we propagate activations and parameter gradients through the network until the first layer. Finally, with the parameter gradients which have been computed, we update the parameters using some form of stochastic gradient descent. This training process is generally parallel. This is also done because of memory, but the main interest in parallelizing training is an increase in the throughput of training. There are two main categories of parallelization approaches. The first one we can call distributed training. The idea is to increase the number of gradients being computed on by replicating the model on several devices. In data parallelism, the more standard approach, we compute each device will compute its own microbatch gradient, and then we will, when all of these gradients are computed, they are averaged and communicated between the devices, and the devices will locally update the parameter using the average gradient. Note that here, the parameters of the models are thus kept all synchronized. The orthogonal approach to parallelism is model parallelism. The idea is not to increase the number of gradients, but to increase the throughput of the gradient estimation directly. This is done by splitting the deep neural network's computations into several stages. For instance, in pipeline parallelism, layers will compute on a subset of the mini batch, the micro batch. So each layer will be able to compute on a micro batch separately. These two types of approaches still have their limits, and we can parallelize even further than approaches like data parallel or pipeline parallel, but this requires changing the training algorithm from one which is equivalent to training on one device to a more complex one. First, let's discuss the issues with distributed training as done in data parallel. The problem is that communications are costly inside the data parallel. We can even slow down training since we need replicas to wait for the last device to finish its computation before starting the communication. Similarly, we must wait for communication to finish. This is a problem since communication can become a bottleneck as we increase the number of replicas. This increases the communication volume since we need to communicate more gradients at the averaging step. Still, we can limit communications, but this comes at a cost, which is to breaking the synchrony between the different replicas. This can still be actually a benefit if we exploit this diversity, for instance, in the case of ensembling. By ensembling the predictions, which means averaging the predictions of these different models, we can make a more generalizable system. It's also possible to avoid the increased inference cost of ensemble learning by possibly merging the models. But to merge the model with a performance similar to ensemble learning, this will require careful communication. Therefore, in both opposite approaches of distributed training, we observe that communications remains the main bottleneck. Therefore, our first research question will be, how can we improve both synchronous and ensemble training approaches with more communication efficient techniques? On the other side of parallel approach is model parallel. In model parallelism, the main bottleneck here is backpropagation. As Jadorbeck told them, backpropagation induces computational locks, meaning that a layer trained with backpropagation will be backward locked. It must wait for the backward pass of all subsequent layers before being able to update its own parameters. We can search for different training algorithms which do not have such limitation. One of such is local learning. In local learning, every layer will compute one gradient from its local loss. Thus, there is no need to wait for subsequent layers anymore, since you do not need to propagate in the below layers the gradients. However, by removing this feedback from later layers, this generally results in lower performance. It is generally what is called a greedy behavior, since the activations which are optimized locally will be generally suboptimal for later layers, since they do not take into account the rest of the network. Here, then, the problem is clear. We can wonder, is it possible to improve the backward unlock model parallel approaches to achieve performances which are comparable to the traditional backpropagation? We can summarize our contribution in the framework with other contributions, other frameworks, other parallel frameworks. At the bottom of the parallelization capacities are the first approaches that we discussed, data parallelism and pipeline parallelism, which are of which the training algorithm is equivalent to training a single device. By removing some communication volume or estimating gradients which are more different than the one estimated in backpropagation, we can increase the parallelization capacity of our system by moving toward ensemble training or local learning. Here, we will propose novel communication efficient approaches to distributed training, in particular with ensemble training and data parallelism. And in the case of model parallel, we will try to improve backward unlock learning with a particular focus on local learning. Our presentation will be divided into 4 contributions, the first 2 being related to local learning and the 2 second ones to distributed training. Our first contribution is preventing dimensional collapse in contrastive learning with subsampling. First, let's explain what is self-supervised contrastive learning. The idea, as machine learners know, the data we get is often unlabeled, meaning that you do not have a direct description of the data you have. So I don't know that this image is relevant. In this simpler framework, on which we're going to focus on, the idea is to get two views for each image. So with data notation, we can get a grayscale image or highly saturated one of this image. These two views will make one positive pair. All other pair of views, such as one of the cats and one of the dog, will be a negative pair. From these views, we first encode this view through the deep neural network, and then through a small local projector network. This gives a representation Zi. In contrastive learning, thus, the objective will be to bring positive representations pair closer, while keeping negative representations farther away. To achieve this, we use the following loss, with one positive term at the top and negative terms at the bottom. We first propose to adapt this simpler framework for local learning. Using local projectors, we can use them to split the network computations into different stages. In these stages, we say stages as a way to describe sets of layers. So here, a stage is just composed of one layer. So now the local simpler framework becomes to just project the stage activations with the local projector networks into the stage representation Zi. These stages will now follow the following local loss, where the only thing that changes from before is that we have the index of the stage. However, when training this way, we observe a very important performance drop. This is due to the greedy effect, which seems to be the same one as was observed earlier in supervised learning. So we will try to better regularize local losses to improve this performance. And for this, we will follow two motivating ideas. The first one is an idea of using curriculum learning with an oracle. Consider an oracle, which is a network that has been trained end-to-end on the same task. With this oracle, we are able to say that we only want to keep simple examples for the oracle in the local losses computation. The idea being that we want local layers to only train on simpler tasks to produce more simple features which can be used for later use. This idea does improve greatly performance, reducing the gap in backpropagation. However, this approach is not really local, which kind of defeats the point of our method. Therefore, we're going to look at another motivating idea, which is looking at the toy linear model. If we consider Gaussian data X and a linear layer W, with the representation just being W times X, it is known that if we apply strong augmentations only on this the dimensions 8 to 16, there is a dimensional collapse of the corresponding columns of W and of Z. We note, however, that this can be remedied by only keeping examples which are close already, so with high similarity. So using the framework of the curriculum learning and our observation in the toy linear model, we propose in this paper to prevent dimensional collapse by removing examples which are too far away. More precisely, consider that now we have this indicator value alpha at stage G for a pair I and L. Then this value will be equal to 1 if the similarity between the stage representation of I and stage representation of L is over a certain threshold T. This gives the following subsample local simpler loss, where once again we just have added these two indicator terms, this one for the positive and this one for the negative. For the training framework, we'll only consider residual network, trained either with backpropagation or divided into 4, 8, or even 16 series. We consider standard image-fitting dataset and do linear supervised evaluation for the representation. And we can observe that indeed, as we said, the local learning decreases importantly the performance. However, by adding our subsampling, we do find that we can increase the performance of that we obtain and regain a bit of the performance lost due to local learning. Not, however, but adding some sampling to the end-to-end so backpropagation case do not improve accuracy. To better understand why this is the case, we can look at the dimensionality of the representations. Here, we represent the normalized spectrum of the stage representation after each ResNet layer. In particular, we look the representation at the end of the network. Here you can see that when training with local learning, we have compared to the representation of when trained with the backpropagation in orange in the dotted line here, the representation is much lower, which seems to indicate a dimensional collapse, the same type of problem that we observe with the toy linear model. However, by adding some samplings with the full line, we observe that we can reach back a dimensionality close to the one of backpropagation. You can also observe that we increase also the dimensionality in the backpropagation case. However, since we do not have a dimensional collapse in this case, this increase in dimensionality does not translate to an increase in performance. Therefore, here we have observed that local loss regularization can be used to prevent the dimensional collapse of the activations. However, this only removes a part of the performance gap that we can observe with backpropagation. You can wonder if we can use a computational trade-off. Maybe by adding back some feedback information, it will be possible to obtain better performance and reduce the gap locally. This could come, however, at a cost with a real increase in computational locking, which is precisely the problem that we want to avoid. Therefore, it will be better if we can do this without the backward pass. This is the idea that we focus on in the next distribution, which is can forward gradient match backpropagation. In this work, we will focus on forward mode automatic differentiation, or AD. First, what is reverse loss AD? Is just another word to describe backpropagation, meaning that we will do the gradient computation starting from the loss toward the input. This can be made more clear by looking at the gradient computation as a product of Jacobians. And look that by doing backpropagation, we are doing this product starting from the output towards the input. Then we can wonder, is it possible to simply do it the reverse way? And this is what is done in forward mode automatic differentiation. However, this is not viable, because this computation in the reverse order will scale with the number of parameters. Still, we can mitigate this by not computing directly the gradient, but only computing a directional derivative of the gradient, meaning that we will not have gradient of f, but the scalar product of gradient of f with a tangent direction v. This can be written as a Jacobian vector product. So we have our tangent v, and we use it to collapse directly with the first computation as a start, making it much more computationally viable. And at the end, we obtain the product between v and our gradient. The idea of our gradient, thus, is to do a gradient estimate in a single forward pass. More precisely, by getting a random tangent direction v, which must have a zero mean and mean variance, then the rescaled version of the tangent vector with the directional derivative will be equal to a non-biased estimate of the gradient of f. However, note that this estimate has a very high variance, which will scale with the number parameter, making it, once again, not viable. Our main idea in this work was mainly to wonder if you could propose better tangents. In particular, by using local loss gradients, we could obtain potentially gradients which are already somewhat aligned with the same ones we obtained for the backpropagation. Since we are trying to minimize the same objective, they could be aligned. In general, we are going to do an experimental study on the convergence of our gradients. We observe first that we can vary the guesses and target directions, with the target being the loss gradient that we want to approximate. So as we said, if we just want to approximate the rest of the network, we can say it's a global target. And we can also just try to approximate a local loss. As an intermediary, we can propose an intermediate target, which is just a local loss, but one stage away. We can also vary the guess, so the tangent direction B, which can be a random direction, which provides an unbiased first with high variance estimate, or a local guess, which is a gradient from a local loss, which is biased. Once again, as an intermediary, we can propose what we call an NTK guess, which is a local guess, but using a randomly initialized parameter. Here we give an example of our process when using a global target and a local guess. So here we want to update the parameter of stage FG. We have a small auxiliary network, so the same thing as the projector that we considered earlier, with a local loss. This local loss will give us one guess with its gradient. Then you can do a Jacobian vector product between the guess and the target, which is the rest of the network. This gives us a scalar value, which is used to rescale the guess to obtain the estimate, which is then used to update the parameters of stage Fg. More precisely, we can either directly estimate the parameter gradient of the stage, which is what we will call weight perturbation, or the activation gradient at the stage of the output of the stage. And we will call this activation perturbation. Then in this case, we can just backpropagate through the stage with the estimated activation gradient. We will use a different model divided in 8 or 16 stages, different image classification datasets, and also 3 different types of auxiliary network, a combinational one, a multilayer perceptron, and a linear one. We'll always try to have the compute of this auxiliary network be negligible compared to the compute of the stage, as to not impact it. Our main findings with the global target are that local guesses outperform over guesses, reducing the gap with backpropagation for forward gradient approaches. We also observe that random guesses do not converge, and observe here. NTK guesses do not converge either, but they still obtain better results, generally, which seems to indicate that the bias of using a gradient from a local loss seems to be an improvement. In general, we find that the accuracy seems to improve with bigger stages and thus bigger auxiliary networks, generally when using weight perturbation rather than activation one, and when using CNN or MLP auxiliary networks. For some further findings, we can look at the local losses values at the end of the training, at different stages of the network. So here we give the local loss value at the start of the model and the local losses value at the end of the network. We can first observe that the losses increases with random guesses, which is just another indication to the fact that they do not converge. We can observe that with local learning, the local losses value are very low, very fast, at stage 2, almost close to 0. This is of course logical, since this is precisely the task in which they are trained on, which is to minimize this local losses value. However, when compared with the backpropagation, which is the red line here, you can observe that there is a much slower decrease with backpropagation, meaning that the representations at the earlier stage of the network are not well suited for minimizing the local loss, which is logical, since the goal is to minimize the loss at the end of the network. But we also seem to observe that there is a similar decrease with local guesses, which is in the case that using forward gradient rather than local learning therapy seems to inhibit the greedy effect of local learning. We can also wonder about the other target that we discussed. We generally find a worse accuracy when using local targets, and sometimes, but not always, generally worse results when using intermediate targets, which seems to indicate that it's better to focus on estimating the global target, despite this training objective being bigger and thus harder to approximate. Finally, we can also wonder about our first initial hypothesis. How good is actually the estimate? We can do this by measuring the cosine similarity between the local guess and the global target. This gives the following graph, where we can see the alignment for a different state of the network, at different epoch, and with different auxiliary networks. Our general findings are that they are higher. The alignment is much higher for later stages, which is the y-axis. This is, of course, also logical. Since we have local losses which are much closer to the target, their training objectives are going to be much more similar. We can also observe that the alignment varies with the auxiliary network and the perturbation chosen. In general, we find better alignment for CNN and MLP auxiliary networks and for weight perturbation, which seems to correlate with their performance than the performance that we obtain. Finally, we can also observe that after a quick increase at the start of training, the alignment will tend to decrease as both the global and local objective converge to their local optimum. But the main thing that we observe here is that even this week, we observe a consistently positive alignment between the local guess and the global target. So this confirms that our first idea seemed logical, but we can wonder if we can push it to the maximum. What if we had access to the entire local gradient subspace? Will it be enough to reconstruct the target values? Well, we can do this as an approximation by projecting the network on the entire guess batch, which improves, of course, the estimate. This will improve accuracy, but the gap in backpropagation remains. This is a showcase of the more general alignment issue of local learning, which is that the objective, the global objective and the local objective are not aligned enough, in particular for early layers, which inhibits the local learning approach. More generally, we also observe that the performances of local learning are very similar to the ones of forward gradient with local losses. Therefore, which seems to indicate that there is no real point in using forward gradients, since it's an approach that is more computationally locked than local learning. But maybe just for now. Maybe when the alignment issue is reduced with better local losses, with better alignment of early stages, we could use forward gradient to bridge the remaining gap with backpropagation, since as we saw, it seems that we do not have a beauty effect as strong with forward gradients as we have with standard local learning. In conclusion for this part, we have observed that local learning is indeed well adjusted for forward gradient approaches, reducing the gap by propagation. However, the alignment issue that we observed in our first contribution is also a problem in this case. After studying local learning, we now turn our focus to our contributions in the field of distributed training. Our first contribution is cyclic data parallelism for efficient parallelism of deep neural networks. It will tackle the limitations of data parallelism. So as a quick reminder, data parallelism, at each step, n replicas of the model are used to compute each one microbatch gradient. These microbatch gradients are then communicated using a non-reduced operation and average for updating. This gives the following standard update rule. There are several drawbacks with this approach. First, because it uses synchronous communications, there is a need, as we said, to wait for the slowest worker to finish its computation before starting the averaging step. Similarly, this communication step must need to be finished before starting once again. This is an issue since the communication volume and the activation memory, both critical values, will increase linearly with the number of workers n. We also find that the synchrony of execution will exacerbate these issues. As we represent here the timeline of execution of key microbatches in data parallel. Observe here that, so the three colors representing the three microbatches, they will simultaneously do the forward pass the first stage, second stage, and third stage, thus reaching at the same time the end of their forward passes, and thus the activation memory of the system will peak. Similarly, they will do the backward pass to the third, second, and first stage simultaneously, reaching it at the same time, and thus the workers start communicating at the same time. Our main idea here will be to execute each microbatch sequentially rather than simultaneously. This gives the following slightly confusing timeline execution, but we will explain it. Observe here that nothing has changed in the case of the first microbatch. We will have an alternate between 3 forward passes and 3 backward passes. The only thing that changes here is that our second microbatch will start its execution at time step 2. Here, once again, we just alternate between 3 forward passes and 3 backward passes. Finally, once again, for the final microbatch, we start our executions 2 time steps later, resulting once again in the same execution. This gives the following ribbon of intertwined executions. And not something is that we do not have, compared to previously, any superposition of the microbatches, meaning that at every time step, each stage is computed on only by one worker at a time. Thus, at every time step, we will have a constant activation memory. We will just need to be able, for instance, here to hold the activation memory of one microbatch at stage 1, one microbatch at stage 2, and one microbatch at stage 3. However, due to this offset in the computation, some gradients will be computed on using outdated stage parameters. Indeed, if we do the logical approach, which is to do the same thing as in data parallel, update parameters every 2n steps, then all stages will already have started computing with outdated parameters during the updating step, meaning that this will result in the standard one-step delay update rule, where the only difference is we have t-1 rather than t. We can do better than that by making better use of the parameter update. By updating stage parameters individually as soon as n stage gradients are computed, we will obtain a better update rule. More precisely, here, so compared to previously where the update barrier was the same one at the end of the time step, now we will have one update barrier at the end of stage 7, step 7, 8, and 9. With this approach, we obtain the following update rule, where approximately half of the parameters are delayed and half have been updated. More precisely, you can observe that for stage 3, all parameters will already be up to date, while for stage 1, as represented by this post disk, these 2/3 of the parameters used are delayed. Note also that with this approach, we can propose an efficient communication scheme, using only at every time step point-to-point communication and no collective operation like an average. We can just pass at every time step the gradient to the next micro batch that will require it to compute the average gradient. This is pretty much a variant in the standard ring-based all-reduce algorithm, but balanced for the entire training step. Finally, we can use this cyclic implementation in other parallel implementation. Consider first the case of the quite theoretical case where we have one GPU on which we do data parallel. Our goal is not to focus on the communication, but on the total memory. Then we can reduce by half the memory required by the system. In the more standard multi-GPU data parallel approach, we cannot make use of this balance in memory. However, we can make use of these balanced communications when no only point-to-point communications are required every time step. If we add some model parallelism to this data parallel approach, meaning that here we will have each stage being computed on by one device separately, we can make use of this memory improvement and reduce by half the number of GPUs compared to the naive approach. If furthermore we can allow devices to be heterogeneous and hold more activation memory by one micro batch, this collapses back to the case of pipeline parallelism. Finally, we consider also the zero DP approach. In it, it's a variant of the data parallel algorithm. The parameters are not replicated across all devices, but the parameters are shared across the devices, meaning that the parameter of stage 1 will only be on the first device, etc. Thus, normally in 0DP, you need to broadcast and reduce the parameter of the gradients at every forward and backward step. In this cyclic implementation, however, there is no need to do this operation, and you just need to pass the parameter and its associated gradients to the next device that will require. Finally, we made sure that our new update rule will not affect convergence. We observe in particular the CDP v2, so our half parameter update, will improve the standard delay rule and obtain similar results than back propagation. We can also infer the memory improvement that we will get with a perfect implementation of cyclic data parallel by looking at the memory taken by a forward-backward pass of one residual network here or DIT transformers. And we observe that for a network like a DIT, which has much more homogeneous stages than layers, we will get much closer to the theoretical halving with a 42% possible increase in memory. This is due to the residual network with having activation shapes which vary during the time, during the day. In conclusion, here we show that we can improve data parallel by balancing the computations and communications. Still, we are limited by the synchronized computations and the communication rate. Therefore, we can wonder This can now reduce communication, so allow the parameters of the models to diverge, but use this divergence to our advantage. This is what we focus on in our final contribution, which is WASH, train your ensemble with communication efficient weight shuffling, then average. The idea is to focus first on the ensembling. The idea is that you have networks that may have been trained in parallel, but with no communication. It's possible to average the parameters to obtain a more highly performing network. But this will require more inference passes, which may be a problem in particular for on-device implementations. Therefore, it's better if we can merge the population into a single high-performing model. It can be done by just simply averaging the weights. It is known that if the weights of the parameter of the model are close enough, this averaging will be a good approximation of the ensemble. However, if they are not, we say that the models are in different loss basins, and the performance of the average model will be close to random. Thus, we observe that to train an ensemble that can be merged, we must control their weight during training as to not let them diverge too much. This will be done with communication, and therefore there is a trade-off between performances and communication. There are already some existing approaches which do this type of ensemble training, like DART and PAPA. We can summarize in both of these approaches in this way. We have n replicas of the network, with each of their parameters theta n. They are trained in parallel on the same dataset. But then, every optimization step, we will communicate and compute the consensus theta bar, which is just the average of the parameters. Then we can either, in the case of DART or PAPA, replace the weight by the average. So theta n will be only equal to theta bar. Or just move them towards it with an exponential moving average, as in PAPA, where now theta n will be equal to alpha theta n plus 1 minus alpha theta r. In both cases, we need to do regular communications to compute the consensus. Our main idea will be to propose a novel and more communication efficient weight shuffling technique. Our idea is WASH, weight averaging using parameter shuffling. The idea will be to, after every optimization step, we consider every parameter I, and with probability P, sample permutation by I, and shuffle the parameters between the replicas, depending on the permutation by I. In expectation, this step is actually equivalent to the EMA step of PAPA. We note also that we decrease the shuffling probability value layer 1, meaning that we start with the shuffling probability P at the start of the network, which will decrease up to linearly to 0 for the end of the network. We also propose a variant called WASH plus stop, where we also shuffle the optimizer momentum associated with this parameter. We will compare WASH mainly to PAPA, or training model ensemble, since it provides the best accuracies. For the framework, once again, we are doing image classification. We spoke models which vary from 3 to 10 visual networks or PGG. We consider an heterogeneous framework where the replicas are trained with different data limitations and regularization, or an homogeneous one where the only difference is data order. We report the accuracy of the ensemble of all models averaging their weight, or of the average model averaging, looking at the averaging that first the weight and then inferior. We'll have base probability values which are very low, and which make this approach very communication efficient, requiring only a fraction of the communication volume of PAPA. Our main results are as follows. If we first look at the baseline, which are networks that have been trained separately with no communications, you can observe that the accuracy is quite high and also increased with the number of models. However, when averaging these models, since they are not in the same loss basin, we observe accuracies which are close to 100. However, when training with methods like PAPA or WASH, you observe that the accuracy of the ensemble and the average are similar, indicating that they are in the same loss basin. Still, despite requiring a much lower amount of communication, we observe that WASH and WASH-out will outperform PAPA. to get a better understanding on the workings of the watch, we can look at the average distance of each model to the consensus, which is a good proxy value for the diversity of the models, and also if they are on the same loss basis. So the baseline, of course, has the highest distance to consensus. There are no communication between the models, while WASH has a consistently lower distance to the consensus, which allows it to be averaged into a singular model. In comparison, for Papa and Papa Hall, we observe less smooth distances to the consensus, which are much lower than the one obtained in WASH. This can be explained by looking at the steps used by all of these methods. The EMA step or averaging step of Papa and Dart will directly contract or collapse the population distance to the consensus, while the shuffling step of WASH does not directly reduce the distance to the consensus. However, the following training step on the shuffle parameter will result in a constantly lower distance, as we observed here, which allows merging of these models with high performance. Despite these models being mergeable, we observe that the trained models are more diverse, following a more diverse optimization paths, and with higher disagreements in function space. In conclusion, we have observed that by adding some delay in the gradient computation, we can push synchronized distributed training to its limit. And by limiting the communications, but just using a small amount of weight shuffling, we are able to train an ensemble with limited communications that can be later merged. And as a conclusion of this thesis, we have shown here 4 contributions. In the two first one, we improve backward and log model parallel approaches, first by regularizing the local losses to prevent emotional collapse, and by combining them with forward mode automatic differentiation as another model parallel model backward and locked approach. And in distributed training, we have proposed to balance the communications and memory usage in data parallelism. And we have also proposed a novel communication efficient scheme for ensemble training that allows model to be merged with high performance. We can finally offer some perspectives on the subject which we tackled on this thesis. The first one is regarding the problem that we talked about in the introduction. With deep neural networks actually continue growing. There has been indeed some concern about the limitation of training data which is available for such models to be trained, and maybe an over-reliance on the use of synthetic data. Still, for now, it seems that the better lesson, which is to simply increase the compute, will follow, in particular as new directions of compute have appeared in test-time compute, with methods doing several different passes to improve the predictions of the network. Some more orthogonal directions may appear, such as we have seen recently by using AI agents or using memories. Some even more orthogonal directions would be the use of the CPC and training directions for local learning. The first one, which follows on the direction that we have taken in this thesis, is to try to improve the alignment with the backpropagation gradient, either by adding feedbacks in regular computations or with some form of meta-learning. It's also possible to avoid to be used local learning altogether and to simply the use of delayed quantities with the gradients, which is something that we worked on in our contribution called PhD. It's also possible to, rather than try to approximate the backpropagation gradient, to completely follow the different direction and just try to follow alternative, more brain-inspired approaches, trying to do tasks like memorization and prediction, which are more aligned with our knowledge of neuroscience. This seems to be an interesting direction, considering the pre-training losses in a modern financial model, which mainly aim at memorizing and predicting data. Finally, considering distributed training, this field is going to become even more important in the following year, as research and industry lab will need to tackle, as their number of GPUs or TPUs will grow, we need to do trade-off between vertical communications and using some form of delay or desynchronization of the parameters. We also noted that we can use also accumulation in this framework. On another work, finally, in the case of collaboration of training between clusters at different places in the world, more low communication approaches may be interesting in this case, like the ensemble training that we are doing that much. We thank you for listening and thank all the collaborators on this case.
Okay. Thank you, Louis, for the presentation, right in time. So now we'll switch to the Q&A session. So we'll start with the viewers. So we start with Olivier.
Okay.
Olivier.
Thank you very much for the presentation. I would like to say that I really enjoyed reading the thesis. They are indeed so you presented finally everything. So there are clear parts, distributed training, and there are in each part two separate contributions. But overall, I would like to insist that the fact that this forms a very coherent set of work and trying to improve parallelism, to control memory peaks, to minimize the volume of data that is exchanged between the nodes, and in order to the overall goal being to increase parallelism. So that's very coherent. The document is very well written, well illustrated, and it benefits from very good experimental validation, and all the codes also are available, which is very nice. And in each chapter, there is always set of observations, and then build on the literature, the proposal of the new ID, the validation of this new ID, possibly analytically on small toy example in order to justify the approach, and then the implementation and the experimental validation. So this is really the defense exhibited the same qualities in the presentation. I was a little bit afraid by the choice made to present everything instead of concentrating on the technical chapters, but finally you made it, and it was very nice to have this overview of all what you have in your thesis. So thank you very much. Now I will move to questions. So first, two general questions. In many of the solutions that you propose, you consider alternative strategies to end-to-end communication. And so you manage to minimize the memory peak, to decrease the volume of communication, and to increase parallelism. But this is done at the price of sometimes doing accommodations, this introduction of the canvases, and also the second cost is sometimes a loss in accuracy. But because you propose a way to increase parallelism somehow by decreasing the volume of communication and the memory needs, then you can imagine that you can benefit from plenty of old GPUs that could be connected by a bad network and still work. So maybe there is a way to compensate and to say that you are somehow allowed to consider deeper networks, for instance, and to do more combinations because you can better scale. So do you have an idea of how to do this type of comparison and how to compare the accuracy you would obtain with deeper networks?
I guess it would depend on the approach that we consider. In the case of distributed training, for instance, for cyclic data parallel or for ACO or Petra, we focus on the more delayed approaches. Yes, so we have a decrease in performance, but yes, I do think that by regaining the compute that using the compute that we regain with memory and communication costs, we will be able to reach once again the performance that we could lose due to delays. However, in the case of local learning, for now, I don't think that using more computations would help. The problem, I think, too important, too fundamental, which is just the alignment of local losses. We could think that maybe we could, having first done the first local gradient fast training, we could then use it to train the network with backpropagation. And that this combined approach will be faster than doing end-to-end learning. However, this also doesn't seem to be the case because, once again, of this alignment, the local optima and the parameters which are obtained with local learning are generally too far away from the one obtained with backpropagation, meaning that we do not really have gained distance towards the local backpropagation optimum, and that doing local optimum is, will not allow us to reach it faster. So for now, I guess it depends. In local learning, we will not be able to regain the accuracy. I don't think so. The local minimum or the local losses are the problem. But it's still a way to obtain slightly worse but still performing models much faster. In the case of distributed approaches with delays, I think that it should be used. This is actually, in the case of ensemble training on WASH, one of the paper on which we compared to, Papa, did this experiment, which was to wonder, rather than doing this ensembling into one single model, what if we used this compute to train one single model much longer? And they showed generally that this accuracy was worse. It seems to show that it's interesting to do this kind of ensemble training.
Yeah. Thanks. Another general question. Not only, yes, I think it applies to both. You always consider, maybe at the exception of WASH, where your the probability of exchanging weights depends on the depth of the layer. Otherwise, all the solutions that you propose are very static, homogeneous static in terms that it doesn't change over time, homogeneous that you always do partitions with same number of layers, basically. And would that be, and also the choice of being local or global is also a choice that you make at the beginning, and you might imagine to do some epochs with a global approach and to end propagation approach. Did you try to combine all these to make your solutions more dynamic, heterogeneous?
Yes. So first for the second question, which is regarding, I guess, binarity of doing local or global learning, we have tried to accuracy is a bit better, but it doesn't seem to be a good direction to follow in this case. But yeah, there are approaches like this which do propose an alternative between fully local or global learning. And more generally about using very fixed local approaches, we have in both contributions on local learning consider varying architectures or local losses depending on the depth. Something which I even tried was using a linear layer to realign the gradients which are obtained with the local loss gradients, and maybe thinking that maybe by just having different local losses or realign them for earlier parts of the training, it would obtain better results. But this didn't generally appear to be the case. But I agree that just from what we saw, the alignment being much higher for later stages, this just indicates that we need to focus on the alignment of early stages. And in this case, different local losses, different architectures will seem to be required. Even in the case of forward gradient, with the alignment, we observe that the alignment was not always the same between the auxiliary networks, depending on the stage. Sometimes linear layers generally being better aligned for earlier stages. And I agree that this is the direction that we probably need to follow. Something which I also wonder is, so there are approaches to regularizing local losses. It's called Anthropo. The idea is to add regularization loss, which tries to reconstruct the input. So to have one term that is a supervised loss, which we consider, and a reconstruction of the input. So something which I also often try is to follow this idea and to have generally more important values for the supervised loss at the end of the network, and more important values for the more important lambda for the regularization term at the start. We really want to keep information for later in the network. But this generally did not change much the final results. While I think that this is one of the most important things to consider to improve local learning, generally did not change our conclusion in this works.
Yeah. Maybe more technical question. Can you go back to your first to the table at the end? Yes, this one.
Yes.
Where there is memory. I was wondering, so these results are obtained with one GPU?
No, and it depends. For the side pattern, yes. For the STL, and I want to show this to you. Since I had remarks earlier about this, I found that the accuracy required variance. So, and I observed that there was a very old bug inside the distributed approach for, in the case of STL, so which increased the accuracy for every model. So it's not the same value that was in the console. And it also showed that the accuracy that we improved with subsampling is a bit lower than before. So once again, that the with subsampling improves better accuracy in the case of CPAR10 than STL10. And so yes, for STL10 we had to use the distributed implementations, but not in the case of CPAR.
And so, for instance, in the case of CPAR10, how do you estimate the memory? Because it will depend on the scheduling order of the different.
Yeah, this estimation is just estimating, dividing our network and looking at the memory and max required to do forward-backward pass on each one and keeping the biggest value. So at most, for if we do in parallel distributions, each stage will require at most this amount of max input.
Yeah.
But we did not implement it in a model parallel way. It was implemented. The distributed way was just data parallel to each end.
And you can expect that the memory, when using 16 slices, the memory will be closer to the overall memory divided by 16, or there will still be an overhead due to local losses, but only.
For local losses, the overhead is usually quite small. I don't remember the percentage in this work. In the case of forward gradient, we really try to limit it to be fair with the other approaches by having the number of flops being under 10% of the stage loss. I think in this case it's a bit higher, but I will not be able to say exactly. But it's not generally too much a problem of memory, but more of more compute.
Maybe on the next chapter, so you introduced two intermediate
Yes.
methods, NTK and intermediate targets, and in the end, they do not provide very convincing results. The local one always is much better. How do you explain this?
In the case of the target, it's not the local, it's the global target, which is better.
Yeah, no, sorry. Yeah.
And this seems to be, I guess, just simply by approximating the global target, we generally reach accuracies which are relatively close to the backpropagation one. depending on the framework, of course. But when we do a local target, it just means that we are trying to approximate local learning. So we have results which should be lower than the one of local learning. But we could think that the intermediate target, since it has less variance than the local, the global target, but it's also a bit deeper, so you still have an exchange information with different layers, would get better results. But we generally do not have this to be the case. But we measured the alignment and we found it generally higher. But I guess it's just that once again, we are approximating just a value which is lower, a gradient which is worse than the one of the propagation. And for the guesses, for the NTK, I guess it's just that we could, so it's pretty much a random direction, just slightly biased toward by the shape of the network. And I guess it's also because when you look at the alignment, you have generally a very, very low alignment values of the training. So you need your local loss in your auxiliary network and need to learn to be able to be somewhat aligned with your parameters. So by randomly initializing the network every time, we just keep an alignment which is very low in this case. So this explains what we have, why we have performances which are close to random.
On this chapter, also, you introduce at the very end this idea of using several guesses.
Yes.
What is the computational overhead? Several guesses, and up to which dimension you deal with plenty of guesses and larger dimension space?
It's a good question because here we created this experiment by getting the gradient of the local guess and the ones on the backward pass, and then computing the projection. And not, but we could do it with a Jacobian vector product. We could approximate it by, for instance, getting so the entire batch of guesses, doing a PCA or similar operation on it, and getting the major direction, the K biggest direction on it, and then doing K Jacobian vector product with these directions to obtain a good approximation of the projection of the target in this subspace. So I guess it will depend on the number of directions that we consider. It will require more forward passes and more Jacobian vector product, but it will get a better estimate. But since it was more for the experiment, but we found that it didn't solve the problem. So again, we thought we did not talk about it in the paper.
Okay, thank you very much.
Okay,
Yes.
thank you, Olivier. Christian, now we will switch to the second reviewer. Yeah, please.
Yes, thank you, Nicolas. And thank you, Louis, also for the presentation that you made. I also wanted to compliment you on the quality of the report. As mentioned, so on the manuscript mentioned in the report, it was very well done. There were several interesting contributions, which I think you presented very clearly in the cases that are performed, so it was giving compliments to the methods we're proposing. The same quality, I think, Charlie, Olivier also in complimenting you on the presentation, which gave a very good overview of the variety of contributions that. So the slight inconvenience in coming second as a reviewer is that some of the questions which are were taken by the first reviewer, but then I have the advantage also of maybe being a bit more provocative in some of the questions. So I'll start with the first one that Olivier mentioned in terms of the performance, right? So when you go, especially in the local level, the first contribution, right, that you presented, you're also talking about how there is going to this local level approach. There is a first loss in performance, right? That
Yes.
At the end, by proposing your methods, you catch up a little bit. It doesn't come back to where it was maybe without this local approach. So again, I'm saying it's slightly provocative. So would you say that this is the paradigm that you would not recommend people use, or how would you go about say selling this approach?
from what we find, I think this paradigm is a bit of a approach to try to avoid one problem of local learning, which is the dimensional collapse. I mean, we can, for instance, I think it's not a way to get better from local learning to backpropagation. It's not a way to get back the alignment that we lost. Because, for instance, if we look at the values of linear probes when training with local learning, so this is just doing the linear accuracy depending on the depth of the network. When you do end-to-end learning, you find that you have a very progressive increase in performance. But when you do local learning, you have a very fast, really increase in performance. It's supposed to minimize this loss. And then you plateau at the end when your activations are not good enough to improve the accuracy. And if this method was really a method that could be used to start pushing the alignment toward the backpropagation one, what we would expect will be to start having a more slower increase in activation, in accuracy. But what we obtain actually is that by adding something, you just have a constant increase in performance. Meaning that this is not the direction that I would say people to use if their goal is to get a better alignment. But if they obtain an important decrease in performance due to local learning, one of these reasons seems to be a form of dimensional collapse. And in this case, it is helpful to use it.
That's very clear. Thank you. So the second point on the same contributions, I think you mentioned also in the manuscript about how this was all done for the CNNs, not the transformer models.
Yes.
So you mentioned a little bit on that, maybe towards the end in the conclusion. So can you say a little bit more on if you were to take these kind of paradigms for the transformer case, the local, especially, how would you evaluate?
Well, there are several advantages to looking at local learning in transformers. First is, of course, because we do not have the activations that change shape every time. So you can have a single architecture for the auxiliary network, which makes it much more easier to implement. And also, since you have always the same shape, I think it's probably better to find more novel local losses, which can make use of the fact that we are always in the same space. So I started working on it, but for now, we don't find a very good result. Maybe to try to find a way to map the projection at the start of the network of the first embedded space, and then progressively move toward the activation that we want at the end of the network. I had talked also with another student which talked about this approach for the form like a flow machine a bit, where you want to move the distribution from one space to another. And with a transformer, I think it's pretty easy to have them, since it's always the same space, to have them move towards to the space. While for visual networks with varying shapes, it's much more difficult to compare at different stages of the network the activation that you get, which seems to be a problem when we tried that. So I think, and also with the local losses which are used in the transformers for pre-training, for VITs or for this type of network, it seems, since the generative one, I had hopes that it would be better for local learning, since the problem also with the losses that we tackle in the image classification dataset here is that it's a discriminative loss, where you want at the end of the network to collapse your activations to only a few points. But when you do generative tasks like for LLM, you will not have this the same collapse that we can get in this case for transformer. So these are the main two reasons why I think it seems interesting to focus on local learning and transformer architecture.
Now that we are here, maybe, so would you say this is the next thing that you would do if you were to continue working on this topic?
I guess I think there are several projects which I was working on. I think it will be the first one. Try to find ways to find better local losses for pre-training larger platforms.
So another point I think I wanted to make also this chapter and the next one is sometimes I think we'll go back to the point that you mentioned on the that you found. So bugs are good as long as you find them.
Which one?
You said something about the data sets here in your answer in ODA, that you have fixed a bug which changed
yes.
the results.
For certain.
Yeah.
Can
you say a little bit on this? What was the
because of the first implementation for CFR10, we didn't change anything because I was not using a distributed framework. In my own implementation of the distributed framework, which I only use for STL10, even as a small, I think it was last year, renormalization issue, I think, or learning rate, which affected the first.
So this also answers the questions that I had in the report, and also now I noted is that there was some sort of inconsistency maybe across data sets, which I think is not so much anymore now. There's observations are.
We also seen improvements in 8, but still, I agree that it's much lower for STL10 than for CFR10. And I think one reason for this is maybe that since STL10 is a bit harder data set than CFR10, you do not have the same dimensional collapse in CFR10. Where for CFR10, if you have 16 stages where you're always trying to optimize on very relatively simple tasks, this is where the dimensional collapse can appear.
So in this case, I was wondering, so instead of just looking at accuracy, do you think there should be other measures also that we look at? We are comparing memory comparison, but beyond that, can you recommend other ways of looking at this? So comparing your approach to this proposed. It's an open question. I don't know what I do.
I guess sort of the work they did during our gradients, looking at the alignment between the gradients, seeing if we have a better alignment when using this subsampling of the losses compared to the previous one. And the other metric that I tried to add in the lesson, which was looking at the linear forms, to get a better understanding of the intermediate representations, since it's mainly what we are concerned with local learning. And yeah, I guess.
So related to that, I also found, I think it was the last chapter maybe, where you kind of tried a distance between models. So I'm thinking, is that sort of an analysis that can be done also, for local learning and the other contributions that we have?
I don't find a good analogy in the case of local learning. In this case, it was very good analogy for the diversity metric or can be measurable. But I guess the best analogy that I would have would be the alignment, which I guess is a way to measure the distance between the approach of local learning and learning.
So two more questions. So one is, so the methods that you presented, they're sort of inspired or it could also say be limited by, let's say, the current architectures that we have in terms of GPUs and hardware. So if you were to look at the problem the other way, say you're free to change the architecture of all the hardware that is available, do you think, would you propose different kind of methods to exploit that? So
I guess, particularly in the case of local learning, since still, if we want to train local learning in parallel, we also are concerned with the communication between the devices. Generally, will be forward and backward gradient, which are propagated. But in the case of local learning, we always know that the flow of the information. We always just propagate activations to the next layer. And so by having very specific connections between my devices, which I know are just one way. I guess we could make implementation of model parallel local learning and much faster.
So one final question is about, so you sort of have these two paradigms, right, that represent two sets of contributions. So can we sit somewhere in the middle and using a little bit of both the programming and the other aspects? So,
Yeah, but we are generally orthogonal. They are not really, you don't have to choose one or another. I think it's a bit what I looked at the end of cyclic data parallel when I wonder about also adding support to the parallelism to it. Yeah, for local learning, I guess there's nothing that prohibits from doing data parallelism approaches to local learning. And I guess this is also a bit what I want, something that I focused on between cyclic data parallelism and WASH. One of the motivation of WASH was actually thinking about the this parameter shuffling I did. So I did. Yes. Was thinking about data parallel and model parallel together, and thinking that so if we have distributed training and also model parallels, each of these parameters of one device, we thought about an idea, which is that if we do not forward pass or backward pass between the assigned layer, we found that well, you can just have different relations to another layer. It doesn't change the communication cost. It's just means that you are communicating to another device. And this was the start of this idea for WASH, which has to mix data and model parallel to do a stochastic activation routing, which in the end became a way shuffling. It's the same operation.
very good. Thank you. Thank you very much for your answers.
Thank you, Kartek. So now we switch to the designer. So for the designer, Adam, Eugene, you can the floor.
Yeah, thanks. So presentation writing. I'm gonna mostly focus on chapters 5 and 6, the more familiar with the but yeah, I wanted to clarify a bit use of this data parallelism, because you said there's kind of two dimensions, the memory and the balancing the communication, but basically it sounded like the full memory advantages and like defining that is.
Because I think the main thing, so the main thing that we share is just the order of computations inside the and so the forward passes for this echo batch, this one will be not the same. When the memory is shared, we can use the fact that they will not use the same stage at the same time. For instance, the final stage, stage 2, since they are all delayed by the same execution, you can have the first micro batch reaching the final state, finishing its backward pass, and just at this moment, the second batch reaches the first stage. So you can use once again the parameters of the first stage, etc. So you have this sort of pyramid of memory which is required. But what's interesting is that you can share the memory between the different micro batches executions. But this is not the case in standard multi-GPU data parallel, because the memory of each stage is located only on one unit. So you cannot share the final state value. This is not the case as soon as you add model parallelism. In this case, there is no sharing of this of the memory of the last stage. I mean, there is no exclusivity of this stage on one device. You can just share one final stage device.
But in the multi-GPU case, we still have lower memory, so we maybe something to.
I wonder, but since we are doing multi-GPU, it doesn't can't really exploit this. I guess this is the idea of, that we propose of a single GPU. In this case, we can be total expression memory as a sense, as a direct practical sense. We are sharing this memory. Otherwise, I wasn't sure I was going to go to.
So you talked a bit about like the way gradient methods, since you mentioned also like so can you explain a bit how methods like how they're different in their
So yeah, well, different type of delayed approaches. In the case of, yeah, I guess pipe dream is a way to can be implemented in such a way that you have a similar cycle of executions which doesn't stop, but on which you need to use the same which uses two versions of the parameters, and you will have one version of the parameter which are delayed at one step. I think what we propose here is a generalization of the pipeline framework, which is very applied to one type of data possible parallelism. And we say we use this schedule of one forward, one backward, but we can use it more generally for all cases where data parallelism appears. And it will give advantage in other cases, such as a single or multi-schedule data parallel, or in the case of zero DP. And not only in the case of the data.
it does let you balance communication one. Not fully getting the perspective.
The pipe dream just returns to this idea where you have your one stage being on one device, doing the same type of execution. You also need to have devices which are the different amount of micro batches. Where here we focus on having homogeneous devices, one type of micro batches.
So, and in this, you get drop the volumes being done at the end. You should do it like pass.
Yes. Yeah,
So
but
wouldn't that be sort of
yeah, in Python with what they do is they indeed do use a bucket parameter buckets, which as soon as they are computed are used to or communicated, so we can balance a bit the communications. But still, when you do the pipe, this means that you still need to require to reach this step before starting the computation. So you do have a little more room to do your communications, but with the data pipe, you have the entire trace. So this allows even more spacing out of the communications.
So in the results, I saw that CDP is sometimes doing better, and especially like in the internet. So
Yes.
why do you think it's like resonant? Like why do you do that?
Honestly, it's pretty much clear. It seems like in this case, having some form of delay is regularize the loss. Which is, yeah, still a bit surprising since in other cases, it's the delay could be a big problem. But in this case, it didn't seem to be an issue. Still, for explanation of this.
And so there's no hyperparameters.
No, no.
And when you didn't change anything about the grades.
No. What is it?
So you always used here like SPB. Like, you think it's like robust to everything?
With the delay.
Yeah. They got like a warm-up.
But this is really not clear. Particular because in this work, the delay had no effect in the regularizing. But the work that we did with training GPT models, we found that the delay could have a very large impact on convergence. It was not the exact same type of data rule or delay, but still we found that using delay and with an optimizer, the delay was very strong and even stronger but was reported in the. It seems that delay can affect much differently depending on the optimizer, architecture, and things like that. Because in this case, the impact of the delay is mainly at the start of training. If you add some form of warm-up, and this is generally what is practitioners will tell you to do, to force the brain to not have delay at the start of training. We have some form of warm-up, you will not have any effect the delay. But when we try to apply a delay in the case of pre-training GPTs, we found that it was not enough. And the delay could be very impactful in this training. I guess having a good optimizer which tackles the delay could be an interesting show.
So what the doing is you
Resolution a bit. Because I guess what we said about the improvement in communication, for instance, maybe in most cases, it will not matter. It starts to matter when you have a high communication volume, reduce and more communication, which really seems to be important. In this case, this balance may be important. But yeah, we need to do a very effective implementations. I was starting to work on the implementation in the 0DP1. Since it seems like the case of the more interested one, the communication value is high, and it's really main thing. This is annoying in 0DP that you still have a collective operation every stage. It's annoying to have reduce and gather step. But we will not do this in this implementation. It would be my first priority. But yeah, it will depend, the implementation will depend on which kind of framework we want to compare ourselves. I think 0DP will be the.
So do you have any more like concrete you can state about the implementation and which things are
The real thing that is going to be not excellent, but hard, but a bit annoying is having we want still to have very synchronous execution. We want to have very homogeneous stages, so that they all do background and passes in a way that we can get the parameters from one, get the equation from the other, into the other. So we want these operations to be very fast, to not impact the execution timeline yet.
So yeah, without it's like everything sort of it's always it's an advantage. So basically, once you have this implementation, you see any like basically are there any limitations put it another way, if I'm working in like a large industrial lab and I still finding out compute like new reason it's a very efficient.
Yeah, well, I mean, the two main reasons are the one that we discussed, which is possibly the delay. Maybe in some cases the delay will affect things. It's a bit hard to know without testing it directly. And the other problem can be that you want to have very homogeneous communication stages of your network, to make it very variable. And maybe in particular, if you want to divide in a lot of stages, you reach a stage where your stages are not really homogeneous. This is a bit the case that you find in machine learning. Oftentimes you're forced to make a choice to have like one layer on one stage and two layers on. I guess that would be the limitation.
Okay, so then I want some questions about.
Yeah.
So you do the permutation randomly.
Yeah.
Like, did you ever study selecting?
I mean, I guess it's a bit what we do by doing a different shuffling probability layer-wise. It seems to show that it's better to shuffle earlier layers than later ones. But if you mean like having the information about parameters of our workers, which one we want to permute, this full requires actually communicating with values. It kind of defeats the point in this case. You need to know the values between different workers before being able to permute them.
Why do you think it's better to shuffle your layer? It's still pushing.
Honestly, it's still not as clear. I guess the idea is that earlier layers will, as a start of training, will more variance, important parameters that you want to focus on at the start. And if they will impact very later layers. You want them to be to reach a closer consensus, which is not as important for the later layers, since if you have already a good consensus on the earlier stages, it will be easier for the later stages. So you can just decrease the shuffling without any loss in performance. Just mean that you will perturbate the variance, the parameter that's. But it's still not a solution.
So next question is, so you kind of present this Russian ways to get a single model that approximates the ensemble, right?
Yes.
But at the end of the day, I would say what you're really doing is model given to architecture, like a certain amount.
Yes.
So with those constraints, are there like other things that the model is really longer?
So yeah, so as I said before, if you just compare in terms of using the exact same compute to train a single large model in time, then what Papa showed is that it was better to do it this way, to be honest. But still, I guess the main question is that there's other similar approach like before generalization, like the SWA or SWAT, for instance, where you use some of your compute to do a generation, look at different optimization paths and average them. And it's orthogonal, not orthogonal, also to find a better generalizable network. And I guess in this case, they just show that you can use a SWAT performance orthogonally to Papa or watch here. But I guess it could be a question to say how much of the one method do we want compared to the other? Do we prefer to have more models in one case, use our compute to more models to average, or use a bit of this compute to do generalization approaches like SWA or SWAD, which improves generalization directly to the information. But I guess it's something that we need to be measured at find the push.
You go to the
Just a part of the results.
So notice there's some cases where this models like ensemble and ensemble really improve that much. So I mean, so basically, yeah, can you comment a bit on like why the scaling some cases not very interesting. Like for the UDG16, for example.
Yeah, it's not much. I think because if you increase the number of models, you will reach some kind of logistic curve of accuracy. And if you increase a large number, the goal, I guess, of the ensemble is a bit to approximate the global optimum function. And so if you think like of the different optimization paths, which are on the same loss basin, and different approximations around the global optimum, okay, with some a few models, we will get relatively good estimate. And as you increase the number of models in your ensemble, it becomes a point of diminishing returns. There's no real point to having a model to just get a bit closer to global optimum. Every time you add one, just rescale the prediction by one or two.
So there's kind of a limit how much
Yeah.
interacts a lot with distributed rate training pipeline.
Yes, in this case, it becomes clear that if you have a point of diminishing returns for the number of models for this type of value, then you want to start using more orthogonal methods.
Okay. Okay, my last question, can you comment a bit on how you pick the research?
For
Yes.
puis only generally parameter, j'ai value just the training accuracy of the average of the features of the process.
Thank you, Jen. So now we have the floor to Simon Mayer.
Thank you. Yeah, thank you for the presentation. I think it's really nice that you consider two different ways to training. I will start from the second part. And my question is about ensembling. Like it looks like when you shuffle the weights, you can do the noise in the weight training. So my question is, like, do you think that maybe like learning the distribution of the weights might be beneficial rather than the weights?
Yeah.
Can it decrease the size of the overall ensemble and do the patient? Do you have thoughts on this?
Yeah, that's a way to see. It's a way to see the problem that I also wonder, which is to say that so you have your ensemble of models, which all, if the models are closed, each parameter is just, I guess, you have a few samples in the distribution of a few parameters, and you can view this idea like some kind of Bayesian deep neural network, where you have a few samples of your network, different samples, and you shuffle parameters inside them. But I didn't really know where to go with this idea, other than by doing this shuffling of the parameter, you try to get a better estimate of the distribution of the parameters. But I was not really sure. Yeah, maybe it's possible to, if we start to find a way to combine the parameter with like even more application, giving seed values and saying if we consider that this is not type of distribution, this is type of distribution, maybe you want to do the values like this. Or even if you say that the more general weight of the network follow a certain kind of distribution of the entire network, not only the parameter. Maybe it would be better to communicate this information between the models and not directly individual parameter values. That's interesting direction, possibly.
And like in your trained models, haven't you looked at the distribution of weights similar for different services?
Yeah. I wonder, but I was not sure how to do this in a way that is meaningful, because I thought that we need to focus on one individual parameter and its distribution, and I will only have a few values. But I could see how it's evolved in training, but I didn't. Was not sure of a meaningful way to interpret. So I didn't pursue this thing. Yeah, so interesting.
Yeah, thanks. Also about this part, I think it's might be also nice to investigate how the way of shuffling and something like affects some robustness. The robustness
Yes.
in our network, because you reported like accuracy, but actually like the regularization usually used to training that also affects robust models to change of the input data. And I would be really interested to see if, for example, this strategy has some benefits in this direction.
Since the co-generalization, they need to be more robust. Yeah.
Okay, I can move to another part of the second section, and now it's CDP.
Yep.
The question is, if you have a lot of stages, like if you split the model
Yes.
different stages and you use different GPUs, do I understand correctly that like at the beginning, warm-up phase and cool-down phase, you have like some GPUs which are just staying without any work?
Yes, it's a very start and end of the network.
Yeah. So do you see how you could, for example, improve this warm and cool-down phases in the framework?
I don't think they would affect that much training. It's only for one training step. You would have just one mini batch sample, you will get this one step. And in particular, since we observe that the delay is particularly at the start of training, maybe we even have to bite the bullet and do a standard data parallel approach for the start of the network to avoid the effect of the delay. So we should be worse than just the warm-up period of idleness. I'm not sure we can really do better than that. I guess at least it's not like in a more standard pipeline parallelism where you have a bubble of idleness which starts and ends between each training step. Here you only have it at the very first and very last training step.
Assume that you train for a very long time with this percentage. My second question about this part, what if you deal with a narrow network which has very long skip connections? For example, dynamic narrow network that depends on the input can go through one or another part. Mixture experts. Will it be applicable? Do you see some benefits to effects? Challenges?
You mean, is it more difficult to split into stages?
Yeah, I mean, like if you have like skip connections between your stages, so will the same dating readiness?
Yeah, that's something that we wondered when we worked on local learning as a network. Do we have to split the skip connection? For simplicity, we generally removed it, but I don't think it's a problem to have a skip connection. You just need to consider that you have your input size that has doubled. But for instance, if your network, you have if we cut the stages between the skip connection, we will have to have input and output of the stage the skip connection values which are continuing to be backpropagated. So it's just a bit more annoying to consider and to tackle this, but it will not change the as long as this the order of executions remain sequential like this, it will not change the forward of the processes. You just need to consider the this increase.
Small communication.
Yes, but yes, there's an increase in communication.
Okay, thanks. And I in this first part, like for local losses. As I got from my other experiments, global loss is better than this local loss training approach in most scenarios, right?
For whole algorithms?
Yeah.
Yes, yes.
Yeah, so I've been thinking that like, can you see some other scenarios where, for example, with this approach might be beneficial? Like, if we don't talk about the training from scratch, but for example, if we talk about some fine tuning when part of the model is, do you think that this approach can?
That's an idea that we have also thought about, and it's the reverse of the idea that I answered earlier, which was you could think that. So before I said you can do, for instance, local learning to do a form of pre-training, and then fine tune on the with backpropagation to obtain the final model. So yeah, there's also the reverse idea, I guess, to pre-train on with backpropagation to do some finite local learning. But the issue is that the minimum that you obtain with local learning are too different from the one that you will obtain with end-to-end learning, backpropagation. So you don't get the advantage that you generally have, which is that you don't need to move a lot on your fine-tuning step to obtain your optimum. So in this case, if we started local learning, I think it could be an issue that the model will not consider the good minimum, the pre-training minimum, and will try to get very far away to obtain the fine-tuning. So combining local learning and end-to-end learning can be a bit problematic. But you could do local learning pre-training and local learning fine-tuning. I think in this case, it will be a problem.
Combining would mean like, you mean like?
I mean, I one step.
Integrating?
Yeah, I mean, alternating between steps of local learning and application.
Thank you again. That's all for my words.
Okay, thank you, Julia. So before giving the floor to your work on supervisor, I will also take the opportunity to ask you some questions. So thank you very much for the invitation. So I want to explain the present to so I first a question on the self-supervised local learning chapter. So you motivate your approach as a curriculum method. To start from easy example, and this would be my question. So curriculum learning in general, you start from easy example and then you gradually add more complex example. I want to understand you stick on the first stage, you keep the simplest example and then you show that it can help to overcome the collapse problem. So do you think it can be possible to be harder and harder simple?
Yeah. So I went a bit fast in this idea, but it was the motivating idea which we worked on first, which was to use a so-called, so not curriculum learning in time, but not curriculum like in depth, saying that what we hoped was more having simpler tasks for earlier stages and more complex ones at the end. And so what remained of this idea was here just having simpler tasks in general. But what we also tried was having different, I guess, schedule, having harder and harder tasks, simpler and simpler tasks, depending on the depth of the network. And we generally found that it was better to have earlier, more easy tasks at the start, and at the end of the network, harder tasks, which just mean like non-sample loss, for instance.
For example, in your case, you just change the threshold, you have similarity value.
Yes,
on the depth.
simpler in the case that we have less examples to contrast.
Okay.
So in this case, it was more curriculum learning, and it provided better accuracy. But since it was since we only needed to have a simple idea to motivate our method, we just kept this one. But yeah, we by doing something which is even closer to curriculum learning, you can get even better results in depth.
In depth, but during the training iteration, do you think it can be a good idea too?
I don't think so, because the idea of doing this form of curriculum learning is to change the training objective of the local loss. So you want to really restrict it from this bad local optimum that Java gets. Okay, and I think by doing curriculum learning and for some time allowing it to have the full task, we could allow it to find once you get this bad local optimum.
Okay, and also getting naive or general question, so your approach is also motivated by this work that analyze the collapse problem in general end-to-end learning tasks. So I was wondering if you think that your approach could also be beneficial for end-to-end learning.
I think it's possible, because when we see the dimensionality for model trained end-to-end, at the end, we do see an increase in dimensionality. Okay. So I think it could be also used in this case. But just since most simply implementations and similar framework, you don't have such a collapse, we don't consider it for this. I don't think it will be.
Thank you. So regarding the second chapter, so on local losses and forward gradients, so at the end of the day, it seems to remain a very difficult task.
Yeah.
So I was wondering if you, so yeah, this is a misalignment issue that remains during bottleneck that you're facing. And then I was wondering if you think so the alignment in this local guess and local target can be somehow.
Yeah, that's something that we. I tried at first with very simple approach, which was to just have a linear layer.
Yeah.
We start with local loss, and to just train this linear layer with the alignment values.
Yeah.
It increased once again. It increased a bit the alignment and the performance.
Okay.
It was not very good. I guess the problem was
In which data set did you train that?
Spartan, I think. Because, yeah, I guess the problem was not that the local club, the subspaces were not aligned. It was more not the local gradient subspace was not expressive enough, just in general. Just the gradients that it provided was not good. But yeah, something which I also learned, and Fournier did not implement because I was not sure if it was going to be a good compromise, was another idea, which is to just say, rather than updating your local loss parameters, like with the local loss directly, have them be updated depending on the gradient that they return and the gradient that you will get from the propagation. So you will get a loss which will be equal to directly this alignment, and try to update the parameter of the local losses with this alignment loss. So it's a sort of second order optimization method, but still it's required having knowledge somehow of the backpropagation gradient.
Yeah.
So you still need to have some time to have this value. And for now, just did some Tori example, and it seemed a bit too unstable for now to work. But I guess it was one. So yeah, one of the question was, do you just need to change the parameters of the optional network to have them be more aligned, or is it even just loss computed? Because something which I didn't make explanation notation is that we are almost always consider just the supervised loss, the same one that we can give. And so something which we also wondered about was having some kind of mixture of losses, regularizing one, self-supervised one, a supervised one, etc. And have it choose the loss which is more aligned with the objective.
Okay.
And again, it improved a bit the alignment, but it seemed like the problem was more, I guess, the low training objective, which is minimized by the first layers, was still not being represented, the one we consider. We need to find an objective which better represents this.
Okay, thank you. And so last question on the second part. So question there on wash. Just curious. So I think you talked about the diagnostic, wasn't sure. So all the results that you present. So the model are randomly initialized. I think you beyond initialization and what would you if you start the same need on the same initialization?
Okay, so this we do start from the same initialization. Okay. It depends on the for methods like Tata or Dart, they start from different initialization, which is not too much a problem for them since they will of course contract or collapse the university pretty quickly. But for WASH, we generally found it was worse for the accuracy to start from different initialization because the shocking effect is pretty weak. It's a good way to restrict the distance to consensus. But if you start from already far away, it's not a good way to reduce the consensus, I guess.
Okay. But for the baseline ensemble, I think here the very bad result that you have when you average them comes from the fact that they are not initialized from the same seed.
Not even the case. It was generally said that you need to start from the same initialization and it's good enough for them to be average. I didn't find that here in this case. I can remember right. I think they start from the same initialization and just from their different optimization paths, it's enough for them to end up in different spaces. What we consider. Okay. It was a bit surprising, but
Okay, thank you very much. So I will stop them and then we need the floor.
Thank you. Yes, I will just say some quick words, which are confirmed by the way you enthusiastically answer all the questions of the jury. I think that the subject you're tackling is fairly challenging because you started it at a point where there was already a lot of optimization that have been carried out, and you successfully investigate, I feel, two aspects of this optimization, which is basically, for example, how can we just tweak the execution in CPDB, where you basically say you complete the same stuff, but then you rearrange the computation. So you already try to get a little bit beyond what has already been done just by rearranging the computation. And you also investigate approximations, where you say that it could give you a computational advantage, but then you gotta make sure that everything works in place. And as you answered all the question, then I think that it really shows your curiosity and your creativity while looking for solutions. So I'm pretty happy with the final content of this work because this shows that you really try to explore several directions that could be orthogonal, complementary, and conducted, as your first reporter said, conducted experiments up to delivering reproducible codes for your experiments. I think this is a fairly decent thesis, and I congratulate you for that.
Okay, thank you, Stéphane. And finally, I will give the floor to the PhD supervisor, William.
Well, so
First of all, I guess I might get a bit emotional because like this is my PhD. Like great company. Been a pleasure to work with you, and I really mean it. I think I've seen you like making a lot of progress. I was very happy with that. I've been actually impressed by the end of the PhD with the number of submissions you did generics. It's really great. Since I've been working with someone who's been extremely dedicated, that's something I really enjoyed a lot. And I think I mean, that was really a great work. So, thanks.
Okay, thank you. So this is the end of the first part of the defense. So now the jury will deliberate. So I will ask the audience just to leave the room.